Students, welcome back. We were looking at the particle accelerators and the linear accelerator in particular. So let's look at, we were here and we saw that a particle gets accelerated along this line if the alternate cylinders are connected to one terminal of a two different terminals like this. Alternate cylinders, they are joined and then they are connected to the one particular terminal, so that if one is positive, the other is negative, the next is again positive, this is negative, and so on. And we had in particular started with a positively charged ion, and we saw how it got accelerated, and it accelerates at the gap. Now we try to find the mathematical relation between the length of the cylinder and the frequency of the applied AC voltage. So let Ln be the length of the nth length of nth cylinder or the cylindrical nth cylinder or the cylindrical electrode. It should be LTH and TH like this. And let nu n be the, sorry, not nu n, Vn be the velocity in the nth cylinder. So what will happen is that let t be the time period. I'll not write it down, please note it down. T is the time period of the oscillator like this, and f is the frequency of the oscillator. And now the length of a cylinder, this one, plus the gap or the separation between any two consecutive. So this is the separation, this part is the separation between two cylinders. This must be the time in which this cycle completes half cycle. This whole electrostatic, not electrostatic, this RF frequency oscillator, that means this AC source completes half cycle. That means if this was negative, it becomes positive. So this is the time in which the charged particles moves from here to here and again from here to here like this. So definitely we can write that Ln is equal to V into T by 2, because you see what is distance is equal to velocity into time. So you see the time required should be equal to how much? It should be Ln. While it's traveling from here to here, at the time it should become like this. So it should be V should be Vn into T by T2. Again, this is equation number 1. Let the particles, let Vn is the, so here we know that Vn is the velocity in the nth cylinder, and again we can write that the kinetic energy in the nth electrode, that means the nth cylinder. When I say cylinder, I am meaning the nth electrode. They are the same because they are treated like electrodes. I can write that it is half m Vn square, and it is equal to nqv plus k. Now what is k here? K is the initial kinetic energy with which the particle had been projected from here to here. And what is nqv? See, for each gap, actually these are very closely spaced, the faces will be very close to each other. There's a small gap out here. We have drawn it wide just to show you what is happening, but actually one cylinder is very close to the other, like this. So at a gap, what will happen, if V is the peak voltage, because it's a AC source, we'll consider the peak voltage, this one, and it will have a fixed value of the peak voltage, and this V into QV will be the energy gained by a charged particle at a particular gap. Similarly, it will be having a number of gaps, so that when it reaches the nth cylinder, it will have its energy will be NQV plus the initial energy K. So this will be equal to the energy of the particle in the nth cylinder. So we can write it as half mv square, n square is equal to NQV. This is equation number 2. Now, so using the value of Vn in this one, we use Vn from here and we apply it here. So what we get is, we had Ln was equal to, from equation 1, we have this is equal to Vn upon Vn multiplied by T by 2, which can be written as Vn divided by 2 into f, because frequency is the inverse of the time period, like this. This was equation 1. So instead of Vn, what we write here is what we got from the equation number 2. From equation number 2, we have Vn square is equal to NQ capital V plus K divided by M, and there will be a 2 in front of this. This will be 2, like this. So Vn would be under root this. So this would be twice F under root twice NQV plus K on M. This would be like this. So this actually is the relation between the length and the frequency. And you see here, Q is the charge, this is the peak voltage, and M is the mass of the particle. So I think I had written small m out there. So please note that, whether I had written small m or capital M in the last slide. So we have like this. So this is the relation between, sometimes we will be asked to find this relation. So this is how particles are accelerated in a linear accelerator. Actually there are a lot of things to it, like when particles passes from this to this, there is a tendency of particles of going this way. So there are devices and there are methods by which the particles are made to move in a particular line, and this is called focusing. So magnetic focusing is used and many other things are used, but this is whatever I have done today is a very simple explanation or the simple principle of how a linear accelerator works. Now linear accelerators are actually of different types, and we have the drift tube type, which we did just now, and it's also called the Linac, which is a very famous name, and it is quite old. And now we also have advanced version of it, such as the waveguide oscillator. We have the waveguide linear accelerator, waveguide type also is there, drift tube type is also there. So this in waveguide is a type where electromagnetic field is actually established here. So here this was just electrostatic, here electromagnetic, and the electromagnetic wave guides the particle, and this is slightly more complex than the drift tube, but for now, for our discussion in the undergraduate level, we will confine ourselves to the drift tube type only. Now we move on to a linear accelerator, the second type, that is the cyclotron. So we move on to the cyclotron. In the cyclotron, you see linear accelerator, the problem is that now you may ask me what would be the size of a linear accelerator. Linear accelerator's size may vary according to necessity. Linear accelerators used for medical purposes are small ones, but those used for accelerating nuclear particles, for nuclear reaction and to see inside the nucleus and all these things, it has to be a great size, a large number of cylinder used, and so it's not very convenient to use, and it's quite a costly and large energy is required. So this is, rather than this, a cyclic type of accelerator is used, in which is called the cyclotron, and we'll take a short look at it now. In a cyclotron, what is done is that the particle is accelerated in a cyclic manner using magnetic field. How this is done is, here we have, suppose I have a case like this, circular case like this, a case with a circular cross section, and I cut it. Then what will happen? This too will be of D shape, isn't it? So these are called the D's, and so we have this two D's. And you must remember that this is not a flat piece, but it is a hollow shaped casing like I showed here. So we have two D's facing with their parallel faces facing each other, the straight faces face to each other. In the center, so what they are called? They are called the D's because of the shape. So if I name this as D1 and this as D2, and an ion source here is placed at the center. This is our ion source, and they are connected to two ends of a oscillator, so that if one D is positive, the other is at the time negative. And a magnetic field is also applied perpendicular to the plane of this one, perpendicular to the plane of this page, because if it's perpendicular, it will work from north to south, or from south to north, from bottom to up, or up to bottom. So from the back side to the front side of this page, or from the front side to the back side of the page. So we will look at the working in the next part of today's class.